And thank you everybody for joining today's webinar. Um, I'm Will, the Director of Product Marketing here at Predibase, and we're really excited for this one. We're going to be getting started in just a moment. We are joined on this webinar by the team from Upstage. We're really excited to be working with them. They're the developers of the Solar LLM, which, as you're about to learn, is the best small language model for fine-tuning. Wonderful. Tim, if you could jump to the next slide. All right, so a few housekeeping logistics for everyone who's joining. Every line is muted by default, but today's session is being recorded and will be made available shortly after the webinar on our YouTube and through email. So you'll see to the right of your screen, there's a chat. It's a public chat. So feel free, and I love the conversation already starting there. Say hi there, say where you're dialing in from. Feel free to strike up conversations, connect with folks on LinkedIn if you want, but feel free to also ask any questions you have during the flow of the webinar. And both of our teams have specialists in the chat that can answer, do their best to answer those questions live through the chat. We will have a dedicated Q&A for our speakers at the end of the webinar, so not to worry there. And then go ahead also, if you like what you're seeing and want to get your hands on it yourself, you can sign up for a free trial with Predibase, where you'll have access to using the Solar LLM. Also, a couple last logistics. I'm about to put a bunch of polling questions live into the chat. You'll see there's the chat to the right, and there's the polls. These are, public, but they're anonymized. So answer, and you can kind of see what other people are doing. They just help us make sure that we are building the best kind of content for you. So going to go ahead and launch those. And Tim, if you could go to the next slide, please. Great. Really excited to introduce our speakers today. From Upstage, we have Lucy Park, who is the Chief Product Officer and co-founder. We have Dev Rishi from our side. He's the CEO and co-founder of Predibase. And we have Timothy Wang, one of Predibase's excellent ML engineers, which if you've joined any of our webinars in the past, I'm sure you've probably seen Timothy before. So should be excited. All right, and with that, I'm going to hand things over to Dev to kick us off. Thank you.
Thank you very much, Will. And thanks everyone for joining today. We're really, I think, privileged to be working with the Upstage team, who have developed kind of an excellent series of both open source and commercial small language models. And I think, within our platform, at Predibase, we've really become known for helping users be able to fine tune models and also benchmark which models are performant for a range of different tasks. And I think one of the reasons we're excited to do this webinar with the Upstage team is we've really found that consistently the Solar models, especially one of their newer variants, tends to outperform all the other models that we've already done extensive benchmarking with. And we're excited to be able to share a little bit of how we've actually seen those results in practice, and then what was underneath the covers and making that a reality. So if we go to the next slide, I just want to give a little bit of an orientation of what Predibase is and how we think about the ecosystem of small language models. So in our view, I think generative AI has come into the stage in a large way, and a lot of different users have found value by starting experimentation with a large commercial model, for example, GPT-4 or Claude Sonnet. But one of our favorite customer quotes is that generalized intelligence might be great, but I don't need my point of sale system to recite French poetry. Put another way, I think that oftentimes these large models are a very effective way to be able to get started with any individual use case, because you can start to query it just off an individual API call. But oftentimes are too slow, too expensive, or don't give you the level of control you're really looking for to be able to work as a production grade solution. At Predibase, we're very bullish on the future being increasing amounts of small language models that are really optimized and tuned for specific tasks that an organization is going to need to tackle inside of their enterprise. And so if we go to the next slide, we've started to see a lot of the data really pan out why this is the future that we're bullish in. And in particular, I think the three things that we find matter for customers is that cost. So being a factor cheaper than GPT 3.5 or an order of magnitude cheaper than GPT-4, as we're able to get a much smaller model that is able to actually optimize and be used on a smaller amount of GPU footprint as well. The second factor that tends to really matter is speed. On average, being faster than even GPT-4o or GPT 3.5 Turbo on a latency and throughput basis. And then finally, I think a factor that probably everybody in the audience here cares about is really quality. So specialized models that can be kind of in domain and outperform even GPT-4. Now, when I've spoken about this topic before, one thing we found is that people really buy into this idea that small language models will help them on a cost basis and a speed basis. But that final point of quality is where a lot of, I think, users need a little bit of convincing. Oftentimes because that open source model that they've tried just hasn't been as good as some of the larger commercial models. We started to try and prove this out for users back in February when we released 25 different fine-tuned variants of Mistral 7 billion. And we just demonstrated that across a series of different tasks, from everything like news topic identification to toxic comment detection and more, that fine-tuned Mistral 7 billion was actually at least on parity with, but in actually the majority of cases, outperforming a larger model like GPT-4. And the key here was that we were able to fine-tune it on in-domain data, something that was very specific towards the task, and see that the model really would outperform a larger model when it was actually evaluated on that in-domain task as well. We were lucky to go a little bit viral, I think, for this, if we go where we saw the same narrative actually be picked up by a number of different folks within the industry. And I think one of the key reasons this really resonated was because it started to introduce this idea of lots of small, fine-tuned, specialized AI assistants, as Jan LeCun kind of put it, and be able to ground it in real data that demonstrated that small language models actually could go ahead and start to outperform what would be some of the larger commercial and closed solutions. We decided to take this one step further just about a month and a half ago when we released our fine-tuning index. So one of the first questions when we released the LoRaWAN models, which was the set of Mistral 7B models, was, well, hey, what about Llama 3 8 billion? What about Gemma? What about Phi? How do these different models actually compare when it comes to fine-tuning? And so what we've done is publish the most definitive guide towards models that are effective when fine-tuned, especially small language models, which right now we're considering anything under 10 billion parameters. And so what we saw was users were right. When you compared base models out of the box, like GPT-4, GPT 3.5, they vastly outperformed things like Llama 3 8 billion. But when you were able to actually add in-domain fine-tuning, we saw these small language models start to get a lot closer to the top of the leaderboard. And one of the really interesting things is that we've been able to benchmark all of these models on over 30 different tasks and data sets and have a really effective framework for evaluating which models do well. And so what I'm going to do here is hand it over to Tim in just one moment, who's going to tell us a little bit about how do we do this benchmarking? How do we think about fine-tuning in general? What's really gone into the process? And he's going to end with why we're really excited about the Solar model in particular. And the sneak peek there is, as we've run a series of benchmarks, the Solar model outperforms even the rest of these models that exist on our current iteration of the fine-tuning leaderboard. And so Tim's going to walk through a bit of like how we've actually found some of those findings. And then the Upstage team is going to tell us a bit about how they actually built one of the best possible small language models for fine-tuning and why it's exclusively available right now for fine-tuning through Predibase. So what I'm going to do is hand it over to Tim to talk us through the kind of nuts and bolts behind our benchmarking work, and then share some of the early results we've seen from the Solar work.
Perfect. Thanks, Dev. So like Dev said, we, back in February, decided to launch what we called LoRaWAN. So I'm going to give a little bit of a background as to on this and explain just our evaluation framework, how we ended up doing fine-tuning and evaluation, and again, go through the Solar results. So LoRaWAN was the result of hard work across all of the teams here at Predibase. It's effectively a playground in which you can explore these 25 Mistral 7B adapters that we fine-tune on different tasks. And you can see that their performance is at minimum rival that of GPT-4 on the tasks that they were trained for. This technical work unlocked our ability to just quickly train and evaluate adapters on a very large scale that we just had not done before. And this accelerated tempo motivated us to greatly expand upon these experiments, which, like Dev said, we used to create our fine-tuning index later, and we ended up doing adapters for over 30 data sets on, I think, approaching 20 different base models at this point. At one point, even letting just one engineer fine-tune and evaluate maybe around 700 adapters over the span of around 48 hours. So the background to LoRaLand was that we aimed to demonstrate 4 things. One, that smaller fine-tuned models can consistently outperform larger generalist ones like GPT-4. And while this isn't really a new idea, I think this was initially started roughly around 2014, it's a point that's very much worth reiterating. 2, we wanted to show that there's a lot of flexibility in specializing a lot of small models using the same base model. This is a technique called parameter efficient fine-tuning, and specifically we're using something called QLoRa to do so, which I'll go over later. 3, we wanted to just put our money where our mouth is with Predibase and to launch a real, fast, and performance application that serves a lot of specialized models with real-world loads and real-world traffic. And finally, we wanted to show that we could serve all of 25 of these LoRaLand adapters on one GPU using LoRax, which is a technology that takes advantage of parameter efficient fine-tuning to efficiently load multiple sets of adapter weights on just one GPU. So also, as shown earlier, after we launched, we made it to the top page of Reddit, and we were also retweeted by Jan LeCun, which was super cool to see. But just to back things up a little bit, I'm going to give a basic introduction to what adapters are. So an adapter is a small set of trained model weights produced during fine-tuning used to specialize a pre-trained base model. When it comes to fine-tuning LLMs, you have a dichotomy between traditional fine-tuning and something called parameter efficient fine-tuning, or PEFT. In normal fine-tuning for large language models, you take your data sets and you run it through your model and you choose to update all 7 billion, 70 billion parameters, or however many you have. But this becomes very computationally expensive and very slow because you have to keep track of all these updates and then also apply those updates to every one of those weights. The alternative in PEFT effectively says that instead of adjusting all the weights of the base model, I'm actually going to freeze the majority of them. I'm only going to keep a very small percentage of the weights around as updatable, and these are going to be new weights that I fine-tune. This new set of weights is only going to be about 1% of the actual model size, which makes this a far more efficient way to fine-tune. We use LoRa, or low-rank adaptation. This is one of the most popular adapters out there. And in this technique, we introduced 2 new tensors alongside specific layers in this model. Here in the diagram, you see that those tensors would be the A and B tensors here, where A effectively just maps to a lower rank, and then B takes this lower rank representation and remaps it to the original size. In this case, we keep the pre-trained weights completely frozen, and then during backpropagation, you only update these new A and B tensors. I did mention, however, that the technique we used was called QLoRa. This is the last trick that we add to LoRa, which is 4-bit quantization, which makes fine-tuning even more efficient. Again, gradients are still only computed for the LoRa parameters that we set. Essentially, you just store all of your model parameters in 4 bits, and as needed, you dequantize parameters to 16 bits, for instance, BF16, to perform computations in both the forward and the backward passes. And so because the weights are decompressed only when they're needed, the memory usage stays low during both training and inference. Now, why are adapters particularly effective with inference as well? So we have our open source package called LoRax. The traditional way of serving models, or LLMs, is to have one dedicated deployment per model. So in this diagram, you can see that each GPU holds one model for one use case. This, however, is extremely inefficient. When you have something like PEFT and you have adapters to a model, which are far, far smaller than a base model, we can do something a lot more efficient with our GPUs. This is what Lorax does. We take one GPU and we host one base model on it, and then we host a number of different adapters that we can simply hot swap out whenever users need them. We find that we can host maybe about 100 to 150 different adapters on one GPU, lowering basically hardware cost by orders of magnitude. This combination of parameter efficient fine-tuning and Lorax is what accelerated our evaluation framework so much. And now you might be wondering, how exactly did we train and evaluate our adapters? So starting with dataset selection, we selected our datasets from ones that were widely available and are either commonly used in benchmarking or can be used as a proxy for industry tasks. Some of these datasets that reflect common tasks in industry include content moderation or SQL generation or sentiment analysis, among others. And then the more commonly evaluated datasets in research are named entity recognition, such as CON-LL++, or question comparison. All of these datasets effectively just allowed us to view just what tasks adapters would be good at. All these tasks span classical text generation to structured output tasks, classification tasks, so on and so forth. But you might notice that the length of the input text varied pretty substantially across these tasks. We had fairly short texts to really long documents. And some of these data sets also exhibited a long tail distribution, which is why we ended up using a P95 percentile of the maximum text length as a cutoff for which we use as input examples. To make sure that we're being fair to, for instance, GPT-4 and any non-fine-tuned models in our experiments, we had to make sure that our prompts were also very fair. To do so, we made sure that the instructions were clear and task-specific. We made sure to explain the task. We specified output formats, like specifying that we wanted a JSON output. And in the case of more complicated tasks, we also use single-shot prompting. So over there on the right, you can see that for the more complicated tasks, we provided an example in the prompts that clearly shows what the outputs should look like with specific delineators and clear prompting. As for the evaluation metrics themselves, we determined the strength of our adapters primarily using either accuracy for our classification tasks or rouge for our generation tasks. We did have to use some special metrics in certain cases. Human eval, widely accepted for coding-based tasks, is what we use to evaluate our coding-based adapter. And then for GSM-8K, which is a grade school math task, we ended up using a regex-based solution extractor to verify that this adapter was properly producing the correct mathematical solutions. We also had to apply post-processing in certain cases to make sure that all the models were given a fair chance. If GPT-4, for instance, were to return a class name while we were returning a class index, this is accounted for. Similarly, we also added some flexibility in the case of GPT-4 such that yes or no could be mapped to 0 or 1 or true or false. Again, just to ensure that all of our metrics were as fair as possible for GPT-4, GPT-3.5, any open source models that were not fine-tuned. But we're here also to see just why we're so excited to be working with the Upstage team on the Solar model. We were able to use the Predibase SDK to issue a bunch of training jobs at once and use our REST-based evaluation harness to get our results. And here's what we found. Across 31 tasks, the Solar model was able to have the highest performance on any given task 18 times out of 31. So the other two models that we fine-tuned models that we considered here were Phi3 and Llama 3 8 billion, which if you were to take a look at our fine-tuning index, were the next two strongest fine-tuned adapters, and this just by itself already shows why we're so interested in the Solar model, because it's able to outperform its next two competitors pretty noticeably. But the other really cool thing that we wanted to show was the comparison to GPT-4. These are the results against GPT-4 with Solar in purple and GPT-4 in orange. It might be a little bit hard to tell exactly what's going on here, so I'll show the differences as well. this is the difference in score, with the purple columns being those that favor Solar. While there are a few outliers, particularly Magic Coder being the big one, Magic Coder is the coding task that we had, and in all fairness to Solar, none of the small models that we had fine-tuned could really hold much of a candle to GPT-4 in the same parameter class as Solar. GPT-4 is just very, very well trained on coding tasks. But for the vast majority of the other data sets, Solar is just able to hold its own very, very well against GPT-4 once fine-tuned. And the results are just incredibly promising for this model, which is why, again, we're so excited to work with the Upstage team. And speaking of the Upstage team, I think I will now hand things over to them to start discussing a little bit more about their side of the work.
All right. Thanks, Dev and Timothy. Can everybody hear me well? Hopefully. Yes. All right, great. Hello, everyone. How are you doing so far? My name is Lucy, and now we'll be exploring how Upstage Solar excels in fine-tuning. I'm here together with Taehyung, who will be answering some of your questions later on. So let's get started. First, let me introduce Upstage. Upstage is a B2B AI startup based in Seoul and Bay Area. We are currently in Series B, having raised over 100 million. Our flagships are Solar LLM and Document AI, serving a range of customers from SMBs to large enterprises across various domains such as finance, legal, and bio. We have served multiple enterprise customers until now, including Samsung, Intel, Lotte, KT, and so on. At Upstage, we offer a variety of services, particularly for the intelligence layer. We have a base foundation model, Solar LLM, and provide language-specific and domain-specific LLMs. We also have related components that can be used along with Solar, especially for easy document processing. So we are proud that Solar is quite competitive in various tasks, but recently we found that Solar stands out as one of the best base models for fine-tuning. Of course, we wanted Solar to excel at fine-tuning, but experimental results from Predibase were beyond our expectations. So we discussed a bit more within the team about the reasons why Solar is so good at fine-tuning. And today, I want to share some of our hypotheses. But first, let's get to know Solar a bit better. My talk today will cover three main topics. First, we'll introduce Upstage Solar and the reasons behind its creation. Next, we'll discuss why Solar may be an excellent choice for fine-tuning. And finally, we'll present some real-world use cases to illustrate Solar's effectiveness. Let's begin by introducing Upstage Solar and the motivations behind its development. So, as I mentioned before, Upstage is basically an B2B AI startup. We focus mainly on enterprises. What we do best is serving enterprise customers. And while serving LLMs to enterprise customers, we learned that enterprises needed, first, a powerful, second, a purpose-trainable LLM solution, third, that can be easily trained with their private data and securely hosted on their premises. So when building our own LLM, we knew that we should keep these principles in mind. Among these three design principles, the first, being powerful, is probably the most important, which means that the key objective when building an LLM should be maximizing the performance to cost ratio, as our Predibase folks already mentioned. In other words, maximizing the performance while minimizing the cost is important. So regarding performance, many customers ask for above human level, above GPT-4 performance for particular tasks. while being at a fraction of the cost. Touching upon being a fraction of the cost, a very interesting aspect is that the hardware available to our customers is another consideration. So in the enterprise, GPUs are often pre-existing and then LLMs are integrated instead of the other way around, where you will first get an LLM and then get a GPU fit for it. So for our customers, this is another way to minimize cost. And for one of our particular customers, this GPU of choice was NVIDIA A100 40 gig. Actually, pre-existing 7B size models fit into this A100 easily, but our customer also realized that the capacity of the GPU was not fully utilized. So they wanted to maximize the LLM's capacity to compactly fit within this GPU in order to max performance. Then the next question would be, how could we fit an LLM within a GPU? So in the A100 case, how could Upstage provide a 11 billion size model to our customer? So at Upstage, we thought of two options. The first is training a 11B parameter LLM from scratch. But this takes a lot of effort and money, so we wanted to see if there were other approaches. The second option is that we considered is continued pre-training from an existing model. But given the lack of approximately 11B size models available, we opted for an alternative approach, which is depth of scaling, or DUS. So DUS is a model scaling technique developed by Upstage that involves two steps. First, step A, we merge two copies of a smaller model into a larger model. So this step enlarges the model, but disrupts the LLM from its converged point. So then we run step B in order to recover optimal performance, which is continued pre-training. This approach, DUS, allowed us to build Solar, enhancing model capacity without losing pre-trained knowledge. And for your information, if this interests you in any way, you can visit deeplearning.ai on July 13th to see our new short course, Pre-training Large Language Models, which touches upon this topic. So now that you understand how Solar was made, let's discuss why it's particularly suitable for fine-tuning. So we have three hypotheses. And first, I would like to disclaim that Upstage always tries to stay on the cutting edge. But sometimes we don't fully understand every phenomena of our models and techniques, which means we discovered that Solar might have an advantage for fine-tuning. But we don't necessarily know and have meticulously proved why. So that's why we would like to invite the community to explore this phenomena with us. But meanwhile, we do have three main hypotheses to share, and I will walk you through them right now. Our first hypothesis is that DUS, which we just covered, led to superior fine-tuning capabilities. We thought this could be a cause because when you execute depth upscaling, the model's capacity goes up, and without losing pre-trained knowledge, we are assuming that this provides more room for additional knowledge and think that this makes Solar highly adaptable and capable of fine-tuning for specialized tasks. The second hypothesis is related to the datasets. So during pre-training and instruction fine-tuning, we composed a variety of domains and tasks in many different ways. We have investigated significant effort in optimizing the composition of datasets and are heading to find the optimal combination, resulting in better adaptation and performance across different domains and tasks. The third hypothesis that we have regards the optimization. We conjecture that Solar has been optimized as a flat minima due to weight averaging. We think this promotes better domain generalization and alleviates knowledge forgetting during the fine-tuning phase. So those were some of the hypotheses we have for fine-tuning with Solar. Now, let's look at some real-world applications of fine-tuning that Upstage has experienced. So while our Predibase friends showed you results mostly from academic datasets, these examples that I'll be showing you are real-world datasets. So this might give you more information and insights. The first case is about machine translation. Obviously, as our Predibase friends also showed us, LLMs are good at machine translation, particularly when they are fine-tuned. At Upstage, we also fine-tuned Solar for English to Korean translation. To do this, we didn't just fine-tune once. Rather, we used an iterative approach. We started out with a small 5 million token English to Korean translation corpus, filtered inaccurate samples, and retrained with an updated synthetic corpus. This process was then repeated several times to achieve substantial improvements in translation. The result? Solar outperformed GPT-4 and DeepL Pro in the Metaflora's benchmark, one of the most reliable data sets for translation accuracy. The second example is about problem solving. LLMs are very good at problem solving, but not always good at numbers. So math problem solving is particularly difficult. In collaboration with Quanda, an AI-based math education startup, we also fine-tuned Solar for math problem solving using approximately 1 million high-quality samples. And after fine-tuning, Solar showed better performance against Microsoft Tora and GPT-4 and achieved state-of-the-art performance for GSM 8K and math among models under 13 billion parameters. The last example was done from a collaboration project with the Industrial Bank of Korea, IBK. So IBK asked us to train Solar to pass a financial domain exam. Frankly, the problems seemed really tough at first. So we were really not surprised when our initial pipeline with Solar achieved 50 out of 100. But when we applied fine-tuning with 4,000 search results, questions, and answers, we were quite surprised that the fine-tuned Solar scored 98 out of 100, which significantly outperformed the base Solar model. So from machine translation to math, problem solving, and financial domain tasks, Solar has demonstrated its usefulness in fine-tuning scenarios. And that was Upstage and Solar's story. We have touched upon the creation of Upstage Solar, why we think it's good at fine-tuning, and some real-world examples where it was successful. So if you're looking for a cost-efficient, high-performance custom model, please try fine-tuning with Upstage Solar on Predibase because it's really good. And I think we now have some time for questions. Please feel free to ask anything related to today's presentation.
Thank you, Lucy. Really appreciate you walking us through all that. Wonderful. Well, yeah, so we have the rest of the time allotted for Q&A, so please keep putting questions in the chat. We've seen some good ones already that folks from each of our teams have been addressing. So let's see. Just give some thoughts on for everybody. All right, here's one from Petrov. How would you go about doing the fine-tuning with the scope of writing in a particular style? For example, in the style of Seneca, Solar fine-tuning.
I can maybe go about that. Also, are you guys able to see me right now? I don't see my video on. But regardless, if I were to go about trying to fine-tune the scope of writing for Seneca, what I would probably do is have a labeled data set, one in natural, like, for instance, whatever your writing style is, and then have a separate column that has the text written in the style that you want. You would probably need at least a few hundred examples, preferably somewhere in the realm of 1,000 to 2,000 examples. And then just simply fine tune through Predibase on Solar there.
Thanks, Timothy. Folks, is my audio still sounding kind of off for you? Sorry, I just got a comment that my audio is put off.
Yeah, it's still slightly muffled, Will.
Okay, I'm not sure.
There we go. Now it's good.
Okay. Well, if it fades out again, I'll hand over the Q&A to you, Timothy. But yeah, just a quick note: the recording is going to be shared. We'll follow up by email afterwards, and it should be on the Predibase YouTube channel. Later today, tomorrow at the very latest, but probably later today. All right, one question: what sample size do you recommend to get the close to maximum improvement from fine tuning? Really great.
From my personal experience, yeah, this is a fantastic question. My personal experience shows that performance tends to increase as dataset size increases, particularly when you have very, very specific tasks. But generally, I would recommend a minimum of like 2,000 rows, because that's generally when performance will start to stabilize a little bit more. But this does depend very much on what your actual task is. Like I said, it very much has to do with how narrow of a task you want your fine-tuned LLM to perform on.
And Timothy, just to kind of elaborate on that a little bit, what kind of success have you seen with, when people have like very limited data just to get started with fine tuning? Like, does it still make sense, even if you just have orders of 100 data rows to start fine tuning and go from there?
Yes, I would say that even if you have just a few hundred rows, you can still see a noticeable improvement in the model. But again, this will depend on the narrowness of your task. If your task is something that's fairly generalizable already, a few hundred rows might make a nice difference, and you can still see that your model does well. But if you have a very, very niche task, a few hundred rows may not be enough for you to get like exactly the performance that you want. You might still have a few issues where the model is drawing from its more generalized knowledge than the fine-tuned knowledge that you want.
Great, thank you. Yeah, it's one of the things where we at Predibase often advocate for that kind of iterative approach of kind of quickly fine-tuning with growing sets of data as your model gets closer and closer to production, because you can make really great leaps with surprisingly small sets of data.
Mm-hmm.
kind of a follow-up question to that, how do you deal with those kind of fuzzy or not specific supervised tasks? And yeah, maybe are those the best fit for fine tuning? How would you approach those?
Right. So I would say that first of all, data set that's not particularly specific, it's a little bit fuzzy, is maybe not the best approach for fine tuning. One of the data sets where GPT-4 did beat us relatively consistently was MLU, if I remember correctly. That one was one that's a lot more vague. It doesn't have a very, very specific use case, in which case I would say either it'd be better to find a more specific data sets, or if the data set is large enough, simply split it up into different groupings and then use the individual data sets to fine tune different adapters and use those different adapters. Because then the model has only been subjected to that one specific domain. And that generally will do better.
Great, thank you. We had a follow-up question related to the Seneca fine-tuning. And that was, how would you use the rejected field in that data set? Rejected being a bad example of writing in the style of Seneca.
Right. In that case, it's a little bit interesting because in Predibase, we simply have like a prompt column and a completions column. What I would experiment with is trying what I believe is called negative prompting. It's generally used more in the image space, where in the actual prompt to the model itself, you say, here is an example of what I do not want to happen, or here's something I do not want to show up in my final output, and use that there. I personally have not experimented with that myself in the text space. However, I recall that in the image space, it actually makes a noticeable difference in what an image model will generate.
Great, thank you. Here's a great one that I know you have a lot of things to say about, Timothy. Why do we focus on an adapter-based approach?
Oh boy, I love this question. So from like I was mentioning in the presentation earlier, adapters versus full fine-tuning increases efficiency by, well, a lot. I'm not sure exactly how I would quantify that, but it is noticeably more efficient, both memory-wise and speed-wise. You're not going to be able to get, I think from our comparison, we get several times faster in fine-tuning when we do adapter-based fine-tuning. And it also enables the use of Lorax, where, like I said, one GPU is required for each base model, or each fine-tuned model, I should say, in the case of full fine-tuning. If you fine-tune with adapters, you can just keep one base model and one GPU, and then continuously hot swap in adapters as needed. So it saves your fine-tuning costs and your inference costs, and particularly in the case of inference costs, it can save you orders of magnitude of cost in both time and money.
Yeah, so kind of, to build on that, we think for using these small language models in particular, that the adapter-based approach really makes a lot of sense in terms of cost and resource efficiency, because you get to deploy those, much smaller fine-tuned models for each specific task and use case. So, there are other scenarios where something else might make more sense for sure, but for that kind of task-specific small language model, adapter-based fine-tuning and serving, we believe to definitely be a great path forward.
Yeah, there's a question that I see is the adapter-based approach the future of fine-tuning? We definitely consider it to be right now the strongest way forward. And for us at Predibase, we keep on saying the future is fine-tuned. We definitely believe in smaller models moving forward. And at least for the time being, the adapter-based fine-tuning is definitely what we're going to stick with.
And kind of related to that, speaking of Lorax, when we have all of these different adapters that you're kind of swapping in for different tasks, one of the questions was, following up on the question around fuzzy tasks, how do you identify the correct adapter at time of inference? It's like, how do you route those tasks to the right adapter?
So this is another interesting question that's been brought up before as a suggestion for us. People have ask for what they're calling mixture of LoRa's or mixture of adapters as a kind of a play on what's currently known as mixture of experts. Currently, we don't have an implementation of that yet, but where you simply just need to know, like in advance, what you're going to be routing to. But you could theoretically fine tune a model to, given a prompt, route to the correct adapter. And the implementation of that, I don't think is actually going to be particularly difficult. It's something that can be done fairly easily right now. You just simply need to have the proper data sets to fine tune on that says, given this prompt goes with this adapter, this prompt goes with this adapter, and you're able to then just route incoming prompts hopefully correctly.
Thank you. Here's a question from Kuntal. Can we use DSPY or Fabric along with conventional prompt engineering? Timothy, I'm not sure if you're familiar with those.
Unfortunately, I'm not particularly familiar with either of those. So I'm perhaps not the best person to answer that question.
Sure. Well, feel free, Kuntal, feel free to follow up. Either check out the Predibase Discord. That's a great place to put maybe a question like that, and we'll have a broader community able to support you there. Mm-hmm. Question for Lucy: what are the sizes of your Solar model?
Right. I can definitely answer this, but Tyon, would you like to go instead?
Sure. So currently we have sizes of 10.7 billions for our base and fine-tuned versions of our Solar models, and we are planning on expanding the model to explore more cost-effective model sizes in the future.
Thank you. How often do, just something that I've seen other people ask about, how often is the Solar model updated? Like, what does that look like?
Well, we don't have a set date or set period in which we update the models, but we are hoping to release the next version sometime in the future. I don't have a set date for that yet.
Oh, sure. But I feel like I've seen some, more regular than some of those other larger model providers. So it's always, seeing really great performance from it.
Yeah, it's always combined with experiments. We want to be very high performant. So rather than having a particular due date, we do have a particular performance criteria that we have.
Wonderful. Are you guys hiring?
That's to both of us, right?
Yeah, I'll say from the Predibase side, always check out our LinkedIn page for careers. We post, anytime we have a new opening, that's where it goes. Lucy, how about you guys?
Yeah, for Upstage, we're always open as well.
Right. Really love these questions, folks. As a reminder, too, we've gotten some good answers in the polling tab, which is just up and to the right of the chat tab. If you haven't answered those, really appreciate it if you do. Again, they're anonymous, but they really help us, tailor the next webinar to better kind of the audience that we see. Wow. Thank you, Abel. Thanks for Predibase. It's cheap and really great. Wonderful. Kuntal, our LinkedIn's are just search for Predibase and Upstage, and they'll be the first two results. All right. Any other questions for our speakers? Happy to give it another minute or so. We're here until the top of the hour if you want, but if there aren't questions, then we'll drop early. But as a reminder, this recording will be shared out via email and on our YouTube later. Question coming in, sorry if I missed it. For this legal domain, let's say you want to fine tune a model on 1, how to write a legal brief, instruction fine tuning, and 2, how to describe each particular issue in a brief, completion fine tuning. Would you recommend to fine tune 2 models?
Yes. So actually, in both of these cases, I think that's going to be instruction-based fine tuning. One is given a prompt of some specification of a legal brief, like write me X, Y, or Z given this. And then your label column or your completion column would be the actual legal brief itself. And then you would fine tune on that data set. The second one would be to describe each particular issue in a brief would be given this particular brief as your prompt column. Your completion column would be the set of topics in it. And you would be able to fine tune. I would definitely recommend fine tuning 2 different models on that. That's kind of just how narrow each task should be. So you will have one model that's given an instruction will write the legal brief for you, and another model that's given a brief will write all the topics for you.
Let's see, a question. Do we have a particular blog that explains how data sets are prepared for Predibase deployment? I do believe that is covered in our documentation. Right, Timothy?
Yes. So we have I believe in our data set preparation documentation, we have just one area that shows you how data sets should be prepared.
Great. All right. Oh. Any thoughts on the best model for coding Python?
This is actually one, like I said, where it's very difficult to beat some of these large generalized models. However, we do notice that in this case, size actually kind of does matter, where 70 billion parameter models do tend to noticeably outperform some like the 7 billion models. I would say if you're going to do this, take a look at the code llama models because they are specifically designed for coding. The other models, such as Mistral, will do okay, but I would definitely take a look at fine-tuning code llama with Python-specific prompts.
Timothy, I'm curious, just from some conversations I've had with other folks in the field. How about if you have your own kind of institutional coding language?
That one is harder, like I said, just due to the specificity of the task. Because while Python or Java or C++ or whatever, all of these data sets are already out there, and a lot of them and a lot of LLMs have that in their base knowledge already. Company-specific coding languages are not widely available. So in that case, if you're going to fine-tune on generating that, you would need a lot more data than for simply coding Python, for example. From what that would be my gut instinct.
Great. Well, thank you.
I think there's a question that we missed way up, where it says where it's about let's see, what will you be recommending for building an in-domain assistant, for example, in the legal or medical domains? How would you do it?
An assistant for this, it depends on what you want the assistant to do. If the assistant is meant to answer questions about specific domains, then instruction-based fine-tuning is likely your how you would go about it. You would provide different questions to the LLM, fine-tune on the answers to those questions, and you would be able to get a decent model for that. Another option that you could try is to sort your questions into different domains, train a number of different adapters on it, and then take a mixture of LoRa's approach, like I mentioned earlier, where you have an LLM that routes to these other small LLMs. Or if your assistant is trying to do something similar to GitHub Copilot, where you are trying to write something out and then you want it to autocomplete, that would be a completions-based fine-tuning task where given a data set of just sentences or small documents of what you want to be typing out, then we would use like windowed attention to determine what the next token would be, and that would be like an auto completing assistance, for example.
Also, just to add on to that is if your domain is too specific, you may want to pick a base model that is already intelligent in the domain that you're looking for. So that's one thing that you should also not miss on.
Right, having a base model that has that base knowledge is absolutely very helpful. The other thing is you could also consider augmenting RAG with fine tuning, where you have reference documents and then fine tuning on both the retrieval and the output.
Thank you both. All right, I think this might be one of our last questions. What are your thoughts about Snowflake, SQL code assistant for introducing prompts into SQL sentences that take into account the data model or database model of the warehouse? Is that something either of you could speak to?
I think a code assistant for that's, again, a very specific task in where you would have to have a pretty large data sets to fine tune on. If your prompts are like, give me a prompt with these specifications, again, that would be instruction-based fine tuning. If it's more code like SQL completion, then that would be a completion-based fine-tuning task. But in this case, the fine-tuning process is going to be the same as you would for basically any other task. You would just have to have a very significant amount of data in order to do it in a way that would make your outputs accurate.
Great, thank you. Lastly, if I fine-tune Solar LLM on Predibase, who has access to my training data? So anyone using the Predibase cloud deployment, so that's when it's in the Predibase cloud, everything is limited to going through the Predibase cloud. We also offer VPC deployments for folks where that makes more sense, in which case Predibase is only a control layer and doesn't actually interact with your data. So we have multiple deployment options depending on the specific needs of different customers. Thank you, Jackie, for double clicking on that. Great. Well, everyone, thank you for your time and attention. Please, thank our speakers for walking us through all this content. Really happy to have this webinar with the Upstage team. Thank you so much for joining us on this one. And yeah, we are looking forward to our next webinar. You'll see details about that in the next couple of days. But yeah, hope everyone has a great rest of your day or night, depending on where you're dialing in from. So thank you so much, and we'll talk to you later. Bye-bye.
Thanks, everyone.
Thanks, guys.
Have a good one.